So on this bell work, we're just going to simplify this to cube root of 40, and I'm going to use prime factorization for this cube root because, again, we have not memorized the perfect cubes on this. So I'm going to split 40 up, I'd say probably 4 and 10, like this. Now, neither of those are prime factors, so the 4 I will break up into 2 and 2, which are prime, and then 10 breaks up into 2 and 5, which are also prime. And since we've circled the end of each of these branches, this means we've finished finding the prime factors of 40. So instead of writing it as the cube root of 40, I'm going to write it as the cube root of these factors, 2, 2, 2, and 5. So we'll multiply all 4 of these. And remember, here since the index is 3, I'm looking for a triple match, which is these 3 2s right there. Okay, so I'm going to split this up again, except for as separate cube roots. Okay, so I got the first cube root with the 2s, and then I got the second cube root with the 5. All right, so I got 1, 2, 3 2s, and then this cube root of 5 as well, and these are all being multiplied. But again, the triple 2 is important because that means that we're looking at a perfect cube for 2. Now you could multiply those out and say 8, but 8 is a perfect cube for 2. So that's why we just pull this out as a 2 multiplied by the cube root of 5. Now that's it for this one. But as a quick review, just kind of theoretically speaking, if there were some kind of number in the front here, even if it's negative, it doesn't matter. Since we've simplified this cube root of 40, then we would look at the first number here and just make sure to multiply it in the end, okay, which we've seen from the last lesson and also throughout the assignment from the last lesson. You have to make sure you multiply those at the end in order to get your final simplified answer. There's our 2 objectives. I can classify numbers as rational or irrational. And really, these are only visual checks to determine if they are rational or irrational. So we just got to learn a few rules to make that determination, and then we'll order numbers from least to greatest. Generally speaking, we'll change those into decimal values and then make the comparisons. But take 15 seconds and copy that down, please. This is how we determine rational or irrational numbers. Okay, so rational numbers, generally speaking, they're decimals that terminate or repeat. Some common terminating decimals that you've seen before, something like 0.5 or 0.25. You'll notice with these types of numbers that decimals that terminate is that pretty much the decimal ends. In fact, just regular numbers, regular whole numbers, whether they're positive or negative. And by the way, these could be positive or negative. It's not going to make a difference. Negative or positive does not determine rationality, okay? But you could look at a regular number like, I don't know, 4. This one is considered a terminating decimal because you could show, well, I guess zeros here that eventually just end. But I guess zeros you could take forever. So zeros on the ends of these actually do exist. We just don't show them. So technically speaking, a terminating decimal is a different type of repeating decimal. It's a repeating 0 decimal, okay? On the other hand, repeating decimals are decimals that repeat and go on in the same repeating pattern forever. But it has to repeat values, okay, not just a pattern. For example, a very common repeating decimal would be 0.3333. And sometimes what you'll see to show that the numbers continue this way forever is 3 dots at the end. I know in the past, generally speaking, we see something what we call bar notation, which would look something like this. So you may have something like 0.851, and maybe just the 1 repeats, so they would show a bar right there. Or maybe even the 2 numbers repeat, so you put a bar above those 2. On this assignment, though, from what I recall, you're just going to be seeing these 3 dots at the end to indicate that it continues. If they don't show the 3 dots at the end, then we're looking back here at some kind of terminating decimal. So you have to be aware of that. Sometimes they'll make those decimals long, so it looks like it's going to repeat, but without those 3 dots, it doesn't. Now, we're not going to see fractions or improper fractions, but your calculator can show them as proper or improper fractions. Just remember that in fractions, so if we looked at a fraction, you have a numerator over a denominator, and generally speaking, when we put fractions into the calculator, we're looking for that button that pretty much looks like this, okay? So you can actually type in fractions into the calculator, but proper fractions is where the denominator is bigger than the numerator. Improper fractions is where the numerator is bigger than the denominator. And yes, I get the feeling that you guys don't care. I'm just pointing out that you can make these fractions. If you can make a fraction, as long as the fraction doesn't have decimals or other fractions inside the fraction, then it's considered a rational number. That's pretty much all I'm saying. All right, so technically speaking, you could type in like a terminating decimal into the calculator, just push the double arrow button above enter, and it generally will change it back into a fraction, a decimal to a fraction. Of course, it will change fractions to decimals as well, if you care, all right? But again, on the assignment, they're generally going to only compare decimals. Now, there's another way to look at rational numbers, and that's with kind of what we're looking at in this unit is roots. Okay, so if you have the square root of a perfect square, as long as it's a perfect square, and hopefully we remember what those are, well, I'll see if I can rattle them off here. 1, 4, 16, 25, 36, 49, 64, 81, 100, 121, or 122. If we see something that's just the square root of a perfect square, then we know it is considered rational. Of course, you could just type it into the calculator. But we haven't seen how to type these into the calculator. This is what you can do. Okay, so let's look at the square root of some number. Let's look at a perfect square like 169. Okay, I know that's off the list, but if you saw this, of course, it's off the list, so we wouldn't expect you to memorize that crap, okay? So what you're gonna do is you're gonna have to first, in the top left of your calculator, there's a green second button. Right here, that's because we're gonna access the green symbols on the calculator. And then you've gotta find, because we're looking for a square root, it's the x squared button. It is one button to the left of 7 for the calculators we have in class. Okay, now on the screen, you'll see the square root symbol come up when you do that. And then, of course, you just type in 169. That's 3 different buttons. And then you just push enter. Okay. Now, if I did that right in my head, that should be 13. It is. Okay, so right there, the calculator just says right away, hey, square root of 169 is 13. Hey, that's pretty cool, right? However, calculators will also simplify square roots for the most part for us. Okay, so let's look at a non-perfect square, and let's see how that would be typed in. Okay, so let's look at the square root of we'll try to make it easy, something like 125. Okay, so you could use prime factorization or perfect squares to do this, but I really like calculator method, and that was the third method we talked about last time, which I didn't show because I was asked not to by the math department. But here we go. So again, type this in. First off, we'll start with x second, and then you push the x squared button, and then of course you're just going to type in 125. Okay, now 125 may even look like it's a perfect square, but it's not. And when I push enter on this, so second x squared 125, you should get 5 square root of 5. Yep. Boom. So you see right there that the calculator will actually simplify these for you. It will simplify square roots. It will not simplify cube roots, okay? Which is why we kind of have to look for cube roots. But again, it's just prime factorization. Now that's all rational stuff. This one here at the top though, square root of 125, it's not the square root of a perfect square. So this one would be considered what we call, well, I guess it's the opposite of rational. This one right here is irrational, okay? Now, irrational in terms of decimals just means that the decimal, it's gonna go on forever and ever, but it will never repeat or terminate, okay? So Now that we have 5 square root of 5 in the calculator, just right above enter, there's that double arrow button. Push it, and right there you see what I would consider a pretty ugly decimal. And maybe to you there's no such thing as a real pretty decimal, but this one's pretty ugly, okay? So this one is ugly decimal. Now, not all ugly decimals are irrational, but these ones are especially ugly because we see that there's not really a pattern. On this one, I got 11.180333989, and that looks like garbage to me. And I'm a math person, so numbers are usually look pretty good to me, but this one it's pretty nasty. So if you see something like that in your calculator, generally speaking, it will be irrational. But like if you type in 1/7 as a decimal, it's a repeating decimal that just looks really crappy. So decimals that never repeat or terminate. On the other hand, we may look at square roots of non-perfect squares, such as square root of 125. The calculator will simplify this so that it looks pretty, but in the end, like we saw that decimal, 11 point some garbage, it looks like garbage, okay? So these are all visual checks. There's not any calculating that should be required. Unless perhaps you see a square root, type it into the calculator, see if you get a perfect square if you need to. If it is a perfect square, then you're good. If it's not, you may see something like this. On the assignment, they're going to say, here's the decimal, is it rational or irrational? That'll be a drop-down box of its own. I'm just going to circle them on the slide here. But then they're going to give us another box where we have to actually choose the reason for our answer, okay? So we see, what is that, 5 different options. It is a decimal that terminates. And just right there, if it terminates, we know that means it's a rational number. If it's the square root of a perfect square, that is also rational. If it's the square root of a non-perfect square, then that would be irrational. It is a decimal that does not repeat or terminate, okay? If it does not repeat or terminate, that's irrational. Or it is a decimal that repeats, that would be rational. So this is not in any specific order. You may see on the assignment that it changes the order for you, so just be aware it's not always going to be in the same position, although for the slides I'm going to keep it there, okay? So just right here, like the perfect square options, I just don't see any square roots on this, so that pretty much right away you could cross those out, but we shouldn't need it. Determinative 0.05903 and a bunch of 3s. Here we see the 3 dots at the end, meaning that this I guess these 3s are going to repeat. It is rational or irrational. So this, I see the 3 repeating. So the 3 repeats because of the 3 dots at the very end there, which indicates that this one right here is rational, okay? So down here at the bottom, well, what is it? It's a decimal that repeats. So I would choose this option right here, and I could push enter for full credit. Well, here we got a square root, so we're not even looking at decimal, but I know that the square root of 9, and you could put this into the calculator if you like, it's just a 3. Now you could consider that a terminating decimal, but the options that they've given us is that this one right here is the square root of a perfect square, which means this one also is rational. Now, if you think that if that was kind of fast, it's supposed to be. Please do not overcomplicate these by overthinking them. That's when we start to get stuff incorrect, and then we start mixing crap up, okay, which we don't want. I did do some calculation on this one, just to show you that it comes out as a whole number, but technically speaking, you don't have to. Which is kind of how all these ones work. There's not supposed to be any calculating involved. We can just see, are we looking at, in this case, a square root of a perfect square? Well, it is square root of 27. 27 is a perfect cube, but it's not a perfect square, which means that this one right here is irrational. We know that if we're taking the square root of a non-perfect square, that the answer is irrational, okay? Now just again, so you can see, if you were to type this into the calculator, if it was a perfect square, you'd get just a whole value, but you see in the answer you got another square root, which is why this one is not a perfect square. Now you could change this into a decimal, it would look ugly, and those make us feel icky inside. So that's another way that we should be able to tell that that's irrational. All right, take a look at this one. Just take 15 seconds, see if you can figure this one out, rational or irrational, and then determine the reason for your answer, okay? 15 seconds. So this one we see, I mean, first off, there's not even a pattern here. So this one right here, I just say that's a pretty ugly decimal. And the 3 dots at the end does not indicate, or it really doesn't tell us that the 6s are going to repeat. It's just telling us right here that the decimal is going to go on forever and ever. And we don't see any repeatingness in the values of the decimal here. So this one right here is irrational. And it is irrational because the decimal does not repeat or terminate. This one right here is a little deceptive because we see that there is a pattern in the decimal, but patterns aren't always an indicator of rational or irrational. For example, on this one, we got an 8 and then 1 6 right here, and then we have an 8 and 2 6s there, and then you see we're just adding a 6 each time with an 8 right there, something like this. These ones. So this dot, again, the 3 dots at the end here indicate that this pattern will continue. So the next one would have, what is that, 5 6, so that's 6 6s, and then the next one will have 7 6s and so forth. But while the pattern repeats, the values themselves do not. So it's not like just an 8 and a 6 repeat, or 8 and 2 6s or something like that. Okay, so this one right here is considered irrational because this decimal will not repeat or terminate. Now, just the 3 dots right there would indicate that it does not terminate, but that means that we would have to determine if it is repeating or not. But this one does not. This one right here, negative. Remember, negatives do not determine rational or irrationality. Same with 1's place values or 10's place values, anything to the left of the decimal. The decimal will determine if it's rational. Right here, it's not showing those 3 dots at the end, which means this one right here is terminating. Therefore, I would call this one here rational because the decimal terminates. Boom. So ordering numbers from least to greatest, generally speaking, we compare these in their decimal form, even if it repeats or terminates. All right? For the decimals that we're going to see on the next example, they're going to terminate, which is fine. But remember, if you see a terminating decimal, let's look at something like 5.17. You could, if you wanted to, add zeros to the end of that because it is, remember, like I told you guys when we're looking at repeating and terminating decimals, well, we started here with a terminating decimal. It's really just that you have zeros at the end that repeat. So you can put in there as many zeros as you'd like. Not that I think you'd need this many, but you could if you wanted to, all right? So we may fill in place values in the decimal place values just so that we can see matching place values in whatever decimals we see, okay? So that's the first thing we'll do. We'll change them into decimal form if it's necessary, and then we'll compare each place value. We start with the one furthest to the left. Start on the left, and then we move to the right. If they're the same, I tend to just cover them up so I don't have to look at that garbage anymore, and then I compare values to values. I don't really care about the decimal, so eventually I may cover that up, and then like if I did, I could end up looking at something that would be like 17, which doesn't matter because we're comparing digits by place value starting with the left, moving to the right, okay? For this example right here, I'm gonna copy this down just so I know what values I'm dealing with. What you see is that not all the decimals have the same number of decimals, right? Like 9.476, we have the 6 in the thousandths place value, that's 3 decimal place values, but 9.43 only goes to the hundredths. It is okay, just like we saw with the terminating decimals, it's okay if you wanted to show zeros, some of the zeros that, I mean, the 0 does repeat, but it's not always shown. So if you do want to show it, that's fine. And the reason why I'm doing this is so that I have 3 decimal places for all the numbers, like 9.427, it already has 3 decimal places. I don't need to fill in any zeros. But 9.43 only had 2 decimal place values, so I can show that third place value as a 0. Okay, 9.347, 3 decimal places. How about 9.4? Yeah, I'm going to put some zeros onto there so that I can see all 3 decimal places. Why is this important? It's because when we start comparing place values, if I see some empty spaces there, I may forget that there is a value there. Okay, but and I do want to compare place values to place values. 9.38 there at the bottom. Again, I want 3 decimal places, so I'm going to tack a 0 on to the end there as well. Okay, so just like I said, we compare place values starting with the place value furthest to the left, and well, they're all 9s. And even right now, I can take this and pretty much ignore those other place values. See how there's just 9s? Well, they're all the same, so I'm going to move to the next place value, the tenths. Okay, and in addition to that, I'm going to get rid of the 9 so I don't have to look at that garbage anymore. You can see here that I'm also pretty much taking away the decimals because the decimal doesn't matter. We're comparing place values to place values. Decimal could be anywhere as long as I have lined up the place values with each other, just like we saw in the beginning that they were ones, tens, hundredths, thousands, and yeah, the zeros are nice to have. Okay, well, we do see differences here. We got 4s, and you got these 2 3s. Well, the 3s are smallest. They come from these two values, 9.347 and 9.38. So right now, just from those two values, that's all I'm going to compare. 9.347, if I can do this right, with some technology, and 9.38. Okay, well, like I said, we don't really care about the 9s, so we'll get rid of that garbage. But the 3s match here, so I'm going to get rid of those as well. And right here I can say I don't need the 7 because this is the hundredths place value. I got a 4 and an 8. The 4 is the smallest between these two, which tells me that the number that the 4 came from is my smallest number. Which also means that the 8 there is, I'm just going to call it the next smallest. Some people I think would say number 2. I don't really care. My next smallest number. Okay, because I was only comparing these two, which means in my list, I can take those two values, 9.347, that's my smallest, and then the next smallest would be 9.38, boom. And just to make it official, we'll put a comma between those. Okay, so there's 2. I use this one and this one. There's 2 of the 6 values, right? So we need to compare the other 4 values. So again, let's take this, let's move it over. Let's move it over to the next place value, and then I'll move this over to so I don't have to look at the 4s. Okay. Now we already did use this one. Let's see if I can do it. This one and this one, right? So I'm only comparing the top 3 numbers and then the second to bottom number right there. Well, these are all different. So I don't even have to go into the thousandths place value. I can see here that among the values that are showing, 0 is the smallest. And among these values, I got a 2, 3, and a 7. The 2 is the next smallest. Three would be the next smallest, if that makes any sense. And then the 7 right there is the last number, so it has to be the biggest. Okay, so again, where do these numbers come from? Well, 0 comes from the 9.400 that we made. And so that would be the smallest among those, this next set right there, 9.4. The next smallest came from the 2. That was from the 9.427. So that would be the next smallest. I'll put my commas here in a second. And then the next smallest was from the 9.43. And then our final number, the biggest number, 9.476. Okay, now that I got those in order, just throw some commas between them. And we'll call it good.